Welcome to the sequence of really cool videos where I want to go over several examples where we are asked to identify where the function is concave up, concave down, and which kind of possible points of inflection it has. So let's work through several examples. We're asked to find intervals where the f of x is concave up or down and identify points of inflections. I call them POI. Sometimes you can see them being named inflection points. The first example is f of x equals 9 minus 2x times e to the 3x. I even gave you a graph because I like that you guys can have some kind of intuition of what is going on before you start working on the function. So how to know where the function is concave up and concave down? This is how I like explaining the situation to students to have an intuition behind the graph of the function. If you imagine there's a rain pouring down on the top of the graph of the function and the water can accumulate like over here because it's basically a cup shape. It accumulates. Then here the function is concave up. If the water is keep falling down like over here, then the function there is concave down. So intuitionally I see that inflection point should be somewhere over here. Inflection point is the point that changed the concavity from up to down or from down to up. Our job is to identify this point, and when you identify the point, you can claim what is the exact interval where the function is concave up and the exact interval when the function is concave down. For this example, I predict we're going to find only one inflection point. Hint. When you see such questions on your homework or exams and say you freak out, every time you see that you're asked to find where the function is concave up or down, identify points of inflections, know that we're talking about second derivative. So even if you blank out during the test, I always like to say where to start. Always start with the idea concavity and points of inflections are about second derivative. So let's find the second derivative. We cannot jump through the process of finding the first derivative, so let's find the first derivative first. F prime is, in this case we need to do product rule, u times v, a polynomial times exponential function. Derivative of u is -2, copy v e to the 3x plus copy u 9 minus 2x. What is derivative of e to the 3x? Exactly, it's 3 e to the 3x. 3 pops out due to chain rule. And I will keep this function just like that. And now from this I will find second derivative. That one will need more space, so I will go down over here. Now, -2 e to the 3x, when you differentiate that, it becomes -6 e to the 3x. It will be very helpful if you pause the video and try to find a second derivative by yourself right now, and then run the video again to compare the results. For the second part, you need to perform product rule again. Derivative of 9 minus 2x is again -2. Copy 3 e to the 3x plus copy 9 minus 2x. What is derivative of 3 e to the 3x? Exactly, it's 9 e to the 3x because one more 3 popped out and multiplied by 3. Now, we want to find where this function is 0 in D and E. In the literature, you see sometimes they skip the idea of D and E points for the second derivative. However, I want to point out that sometimes the second derivative might not exist, and these points might change the concavity. Even vertical asymptotes might change the concavity, and the function sometimes looks like this. There's a vertical asymptote, the function is concave down before it, and then concave up before and concave down after. That's why we always need to include all those points on the side line. In this example, we're not going to find any D and E points, but I just wanted to point out that that's important to consider. What I'm going to do right now is I'm going to factor out e to the 3x and then collect all the terms that are left behind when you factor out e to the 3x. The first one gives me -6. The second gives me minus -2 times 3, -6 again. The last one I will distribute. If you have a pencil, take a pencil and distribute this 9 into, I keep choosing wrong thick colors, let's do pink, distributed over here. 9 times 9 is 81, and then minus 18x, and that's what I got. Then I will have e to the 3x, and then minus 12 plus 81 is 69, minus 18x, where this function is 0 or d and e. It's not d and e anywhere, so we definitely just need to look for 0 points. Well, the first factor is always positive. Why? Because it's exponential function. The graph of exponential function looks like this. So it's never negative and even 0. The 69 minus 18x, however, will give us a solution, a rule. X is going to be 69 over 18, which is 23 over 6. 23 over 6. And this is the point we're going to use for the second derivative sign line. I'll write down. Right now, I'm gonna do the second derivative sign line. And it's my way to organize the information. If you follow this way, I saw students doing different ways. They were creating tables, they were making lists. Do anything you want, just make sure you organize the information in a clear way so that the reader could know what is going on. I like using a sign line. That's a line where we're going to be checking a sign for some kind of derivative. In this case, it's a second derivative. I'm putting the x 23 over 6 I found onto the sign line, and the moment you find second derivative, here it is, f prime prime, put the result in the box because we will be plugging test points in this result. Test points are coming from these locations. Basically, 23 over 6 divided the whole Cartesian coordinate into two intervals, minus infinity to 23 over 6, and then from 23 over 6 to plus infinity. Theorem tells us that only one test point is enough to check if my function is concave up or concave down on the whole interval. And I'll be doing that. Test point can be anything, and to choose wisely, I want to know what is 23 over 6 is. It's kind of almost 4, right? And if you check, it is almost 4. It's 3.833. So for the test point, I can choose, say, 0 on the left and, I don't know, a million on the right. I like choosing huge numbers because it's just fun to work with them. So if I choose 0 and I plug it into the green box, which shows me the second derivative, e to the 0 is 1, and then 69 minus 0 is positive. I don't care what the number is, I just need to know the sign. Okay, so the first interval is positive. If I choose a million, though, and I'm gonna plug it into my second derivative, minus 18 times a million is a huge number, exactly minus 18 millions. That negative number plus 69 is negative, times positive e to the 3x is a huge negative number. So the original function is concave up on the first interval and concave down on the second interval. That's the original f. If you have troubles, also with colors, I will show that this plus or minus belongs to the second derivative, and then concave up and concave down belongs to the original function f in green. So, and these points were plugged into the second derivative, by the way, just for you to understand. If you have troubles to memorizing when the function is concave down and when the function is concave up, I have a funny way to teach it. So if the second derivative is positive, the original function is smiling. If it's smiling, then it has local minimum where the tongue is. If the second derivative is negative, then the original function is grumpy or frowny. Then the original function has a local maximum at the nose. That's a very cute way to memorize it, and surprisingly, it's a really good way to memorize this information. So that's why I know where the function, when the second derivative was positive, the original function was smiling, concave up. Negative, concave down. Now we can answer the question. The question asks us to identify where the function is concave. Concave up. Interesting. Concave up and concave down. And I just saw recently, very nice notation, CU and CD. Concave up and concave down. The function is concave up from minus infinity to 23/6. And concave down from 23/6 to plus infinity. Since the point, or actually input x, equals 23/6, change the concavity and is in the domain. That's important because asymptote can change the concavity, but it's not point of inflection. But this point is indeed point of inflection because it's changed concavity from concave up to concave down. That is the answer. Would you like to check if the answer matches the graph we had? So it should be concave up and then concave down, and the point is 23/6. My prediction was over here, and actually now we know that it's supposed to be 3.833. Oh, I was actually pretty close. You see, I predicted it is here, but it's actually right after 3.8. It's going to be 3.8 and 33. So this is my point of inflection. Then it should be over here. This is x equals 23/6, approximately 3.833. That's my point of inflection, POI. So it's actually pretty fun to make a guess first and then see how precise we are. And indeed, the second derivative was positive first, so we had concave up. And then the second derivative was negative, so we had concave down. Nice, everything matched really well. The second example, let's go a little bit faster. And you can pause the video and go over this example by yourself and see if it matches my answer. So this is a polynomial, 2x to the 6 minus 7x to the 5. Here's a graph for you. I like visualization of the problem, interesting, to see what is happening. So like I taught you before, can you imagine when the rain will start and when the rain or the water of the rain will fall down? So definitely the rain is keep falling over here, it's keep falling, or it's keep accumulating. Interesting, it's hard to say. But it's definitely accumulating over here, right? So this is, I would say, all the orange probably is concave up situation. But that's a guess, again, it might be wrong. The rain is falling over here, right? So I predict we're gonna have 2 points of inflection. One somewhere over here and the other one is somewhere over here. Let's figure out if that's the case. So I see if this is the complete graph of the function, then I predict we're gonna have 3 intervals and 2 points of inflections. Again, what do? We need to find second derivative. To find second derivative, we need to find the first derivative, which is actually pretty simple. 12x to the 5 minus 35x to the 4. Then the second derivative will be 12 times 5 is 60x to the 4. 35 times 4 is 140x cubed. And when looking for zeros, there is no D&E points here. To find zeros, I would factor out x with the smallest exponent. You also can figure out what to factor with respect to the constant, but you don't have to. X cubed will leave me with 60x minus 140 equals to 0. The first root shows up right away. That's equals to x is 0. And the second one will be from 60x minus 140 equals to 0. So x is 140 over 60, which is 7 over 3. Oh, so we actually could factor out 20. As you can see, you can divide by 20. 60 over 20 is 3. 140 over 20 is 7. So we have those like not critical points. We don't call them critical points when we work with second derivative. But I will create a sine line for the second derivative, and I will put in the green box my second derivative again. Here it is. and I will plug the test points into my second derivative. I have 2 points, 0 and 7 over 3, which is approximately 2.33. And I know I have 3 intervals now, so I will need 3 test points. The first test point I will choose will be -1. The second point, I can choose anything like 1, something simple. And the last point, I still like 1,000,000, 1, 2, 3, 1, 2, 3, because it's just kind of cool to plug big numbers. And instead of actually calculating the number, I just want to intuitively find the sign of the second derivative. So when I plug -1 into the second derivative over here, 60x to the 4 will never change the sign. Minus 40x cubed is changing the sign. Since -1 cubed is negative, negative times negative is positive, so everything will be positive over here. However, when I plug 1, 60x to the 4 minus 1, no, when I plug 1, actually it's going to be just 60 minus 140, and it's negative right away. And the last one is 1,000,000. Well, you know, 1,000,000 raised to the 4th power and times 60 is way, way bigger than 1,000,000 cubed. So I know that the first term will be bigger than the second term, and that's why everything will be positive. Thus, I can claim that the original function f is smiling or concave up from -infinity to 0, concave down from 0 to 7/3, and then concave up from 7/3 to plus infinity. Let's write this down. F of x is concave up, CU, from -infinity to 0, and then from 7 to plus infinity. F of x is concave down from 0 to 7/3. You see, I'm not including those points, 0 and 7/3, because these points actually, at these points, the second derivative is 0. So, and these 2 points change the concavity, and they both in a domain. So x equals 0 and 7/3 are both points of inflection. Wow, that's a very good result. Let's check the graph. Did it match the expectations from the graph or not? Let's see. So, it is concave up from -infinity to 0, so I did not match the coloring a little bit. It's actually concave up like this, from -infinity to 0. Then it's also concave up from 7/3, which is 2.3. It's somewhere over here. Concave up over here. Indeed, the water will be collecting over here if there's a rain falling onto the graph of this function. And then the rain will fall down over here from 0 to 7/3. So 0 is point of inflection. And this point is 7/3, which is approximately 2.33. It is a point of inflection as well. Very nice. The second derivative was positive, then negative, then positive. The function is concave up, concave down, concave up. Very nice. One more example includes exponential functions. Here they are. The function is e to the x all over 4 plus e to the x. I found the graph for you, and I'm not really sure if it's a good graph. Maybe the function is actually doing something else at -infinity and so on. That's why the guess is kind of sad over here. I don't know what to expect. Does it even have any points of inflections? Maybe this is a tricky example and there will be no points of inflections at all? Let's find out. I will first find the first derivative. To find the first derivative, I noticed there's a quotient rule involved. Quotient rule, I always start to perform it by squaring the denominator, not forget to do it later. Now differentiate the top, e to the x still gives me e to the x. Copy the bottom, that's 4 plus e to the x. Minus, copy the top, that's still e to the x. And derivative of 4 plus e to the x is e to the x. Did you do it by yourself? I really recommend you to pause the video and to practice quotient rule by yourself, especially since it involves differentiation of exponential functions. Let's simplify. 4 plus e to the x squared then I will have e to the x times 4 plus e to the 2x. Do you all remember that e to the x times e to the x, that's e to the x plus x, so it's e to the 2x, right? Minus e to the 2x. Nice. These guys actually go away. So I end up to have, I will even write down separately over here, the second derivative is 4e to the x at the top, and then 4 plus e to the x squared at the bottom. And I'll put it in my famous boxes I always used to teach with, and I will use it later for my test points. Very nice. I want to know where this function is 0 and d and e, because d and e points can change the concavity as well. Well, the denominator is never 0. 4 plus e to the x squared cannot be 0, because e to the x is positive, 4 is positive, we're adding two positive numbers and then squaring it. It's definitely never 0. It's actually never even negative, so I will say it's positive. Then only 0 points will show up. Those points are coming from the numerator. 4e to the x equals 0. This is exponential equation. Exponential or logarithmic equations are equations which involve exponential or logarithmic functions. To solve these equations, I need to, what I need to do is, okay, I made a mistake. Did you guys catch it? I made a pause to check out what is going on and why this example is so simple. X equals 0 is not gonna happen. How? 4e to the x doesn't even have zeros. So I was thinking, what is going on? Do you know the mistake? This is not a second derivative, it's a first derivative, okay? That's why it's so simple. We need to differentiate it one more time. So no boxes here. Sorry about that, it's not that fast. So I got excited that we're done differentiating quotient rule, but actually we have to perform it one more time. Second derivative, let's keep going. Second derivative tells me that I need to square the denominator again. So now it's going to be to the 4. Differentiate the numerator. 4e to the x gives me 4e to the x. Copy the denominator, which is 4 plus e to the x squared, minus copy the top 4e to the x. And then when you differentiate the denominator, that's when involves chain rule. 2 goes down, copy 4 plus e to the x, change the exponent to 1, times derivative of the function inside. 4 plus e to the x gives me e to the x. Don't mess up parentheses. Not to mess up parentheses, I will put brackets over here and over here. And this is my second derivative, piece of cake. Yeah, I'm joking, we need to simplify this. To simplify this, I will factor out 4 plus e to the x at the top, and then cancel it out with 4 plus e to the x at the bottom. I will factor out 4 plus e to the x with the lowest exponent. The lowest exponent I see is not 2, but it is 1. So I will factor out this. What is going to happen after factoring this out? 4e to the x from the first term times 4 plus e to the x minus 4e to the x times 2 times e to the x. Close the brackets, right? Seems like I did not miss anything. Now I can simplify this too thick. I can cancel out 4 plus e to the x and decrease the exponent in the denominator. So the denominator now will be cubed. 4 plus e to the x cubed. The numerator will be 4. Let me, I guess, distribute everything. So it's going to be 4 times 4, that's 16, e to the x plus 4 e to the 2x, right? E to the x times e to the x is e to the 2x. Minus 4 times 2 is 8, e to the 2x. Now, finally, that should be the last step. 16 e to the x minus 4 e to the 2x all over 4 plus e to the x cubed. And finally, this is my second derivative. And this is what I'm going to put in the box. Crazy. F prime prime. Okay, not too bad. Still, the idea is the same. The denominator cannot be 0 because we're adding 4 plus always positive exponential function and cube it. But the numerator can have zeros. So I'm going to need to solve 16 e to the x minus 4 e to the 2x equals to 0. Okay, let's do that. For example, I can factor out e to the x, even 4 e to the x. Then I will end up to be with 4 minus e to the x equals to 0. Then this 4 times e to the x is never 0, and actually it's positive. We already have made this point before. 4 e to the x is always positive. But this guy can be 0. 4 minus e to the x is 0. When do you think this happens? This happens when e to the x is 4. This is again exponential equation. To solve exponential equation, just isolate e to the x, so it's going to be equals 4, and then apply log to both sides. Or actually, in this case, you can even use definition. But if you apply natural log to both sides, ln of e to the x gives me x, and then the right-hand side is ln of 4. And finally, this is the point we're looking at. We're looking for. Now I can finally start writing down the sine line for the second derivative. I will put ln of 4, which is the only point we found, on the sine line. I will also identify that this is approximately 1.386. And I will choose test points. On the left, look at the green box where I'm going to plugging it in. In the left, I can choose 0 as a test point. And on the right, I can choose a million again, I guess. So let's choose 1, 2, 3. 1, 2, 3, a million. Why not? You can do 10 if you don't like to be dramatic. So when I plug 0 into this green box, which is my second derivative, e to the 0 is 0 and e to the 2x at 0. No, e to the 0 is 1 and e to the 2x at 0 is 1. So we're going to have 16 minus 4 all over 5 cubed. That's positive. That's positive. Then, actually, I just want to point out the denominator is always positive. So we just need to look at the numerator sign. At million, though, e to the 2x will grow faster than e to the x. So e to the 2x at million will be much bigger. That's why the negative sign will make the second interval to be negative. The original function then is concave up and then concave down. That's my f. And I finally can answer the question. F of x is concave up from minus infinity to ln 4, which is approximately 1.3862. And then concave down from ln 4 to plus infinity. Also, x equals ln 4, change the concavity and is in the domain. So that's point of inflection. And that's the answer. Let's go back to the graph and check if this makes sense. I would always recommend you to check if your answer makes sense, so that you don't actually accidentally answer something which completely outside of the domain or real life problem. So ln 4, which is approximately 1.36, should give me concave up and then concave down. Approximately 1.31 ln 4 is over here. 1.3862. Oh, indeed, it makes sense. So the function is concave up right before that. The waters keep accumulating. And then, you see, it probably starts being like this. Concave down. Interesting. Concave up, concave down. The second derivative is negative. And then it becomes, no, the second derivative is positive. and then it becomes negative after that. And this point over here is point of inflection, the point that changed the concavity of the function. That's all the examples I wanted to go through. All of them are different, have different skills you need to use, like finding second derivative using quotient, root product rule, exponential functions. I really hope you liked the idea of using intuition on the graph of the function first, and if you have graphing calculator in your hands, that's very convenient to use it. And just don't be afraid. Find the second derivative to identify where the function is concave up, concave down, and if there are any points of inflections. Good job for watching this video, and see you next time!